This is the last part for homework 3, process dynamics and controls. So in this part, we're going to derive the Laplace transform of a general time-shifted function with a dead time. And then we are going to use a couple different methods in our code, which I'll just get into that when we're actually coding. And for now, I'll derive that Laplace transform. A way to visualize this dead time, that's not a straight line. A way to visualize this dead time would be, let's say we have our original function, it behaves like this, and then after we take into account this dead time, it actually shifts over like this. So this would be our theta. Our dead time, we're using theta as the variable to define dead time. Essentially, dead time is a lag or a delay in time to observe a change that has occurred. And if we want to take our Laplace transform of f t minus theta, our dead time, and u t minus theta again, except now we have, from taking the Laplace transform, we have e to the negative st dt. And since we want to have this in terms of tau instead of t, we're going to set tau equal to t minus theta and t equal to tau plus theta. So then we can rewrite this time theta to infinity. We have f of tau minus theta, which is, f of t minus theta, which is equal to tau. Same thing for this u. And we have e to the negative st. T is tau plus theta. And this should be d tau this time. And this is going to be equal to e to the negative theta s multiplied by f of s. This is just the transfer, or I guess I should say the function in the Laplace domain. And then this right here is our dead time. And what dead time does is it multiplies the transfer function in the Laplace domain with this e to the negative theta s, and theta is our dead time. So for a general function, f of t with dead time theta, we're left with f s, so that's in the Laplace domain, times e to the negative theta s. That is our Laplace transform for a function with dead time. So for example, if we had a k over tau s plus 1 and we added dead time, we would be left with k times e to the negative theta s over tau s plus 1. The next thing we want to do, since we derived the Laplace transform, we want to determine the Ziegler-Nichols ultimate controller gain and period for a first-order system with dead time of 0.1 seconds, time constant of 1 second, and gain of 1. And then we're going to simulate the closed loop response. And just looking up what Ziegler-Nichols is, it's a tuning method for a controller. It's performed by setting the integral and derivative gains to 0, and you can read this if you do not know what this is. So for this part we have a dead time theta is equal to 0.1 seconds, a time constant tau equal to 1 second, and a gain equal to 1, and that's just our k. This would give us a GP equal to 1 times e to the negative theta s divided by 1s plus 1, because this is our k, this is our tau. And actually we have 0.1 seconds for that, so I should write this as e to the negative 0.1 s divided by s plus 1. That is our GP. Our closed loop is equal to GC GP divided by 1 plus GC GP. For our PI controller, we have GC is equal to KC, so this is the proportional controller portion, times 1 plus 1 divided by tau s. And keeping this in mind, I'm going to jump into the code to simulate what I kind of described. I'm going to copy and paste what we're doing just so I don't forget. And I'm also going to go ahead and put in our import that we usually use. So we're determining the Ziegler-Nichols ultimate controller gain and period for a first order system with these described variables. We're going to simulate the closed loop response. And this is with a proportional and integral controller. And the period that we're doing is the time it takes for a complete cycle to pass. So that'll be between the maximum of the waves. What I want to do first is to find the ultimate controller gain, and in order to do this, we are going to kind of ignore certain, I guess, parts of our actual simulation that we're going to have later. For now, I'm going to put in the values given. We had the dead time, I guess I copied and pasted this, but we have the dead time, time constant, and gain. So I'll actually do it in that order. Theta is our dead time. It is 0.1 seconds. Our tau is 1, and our k is 1. To start off, we need to make a guess for Kc. So I'm just going to guess 10. And we also need to set GC. For now, the most simple way is proportional only controller, setting GC equal to KC. And from what I derived earlier, we know that our process transfer function is the gain times, we're going to have exponent of negative theta times s divided by tau times s plus 1. And our closed loop is going to be GC times GP divided by 1 plus GC GP. Like we did in the last video, we're doing our sim for G closed, lambda t1, 1000 steps we'll do this time, and our dt is going to be 0.01. Our fig is going to be make subplots, as always. We want to add a scatter at x is equal to t, y is equal to h. We want lines, and I'm going to name this the Ziegler-Nichols PI control. Right now we're just using proportional control, but it will include the integral later on. I want to update the layout. We'll title this Ziegler-Nichols closed loop tuning response. The x-axis title is in time, so that's correct. Our y-axis title, I'm just going to say, is the process variable. I'm going to do the usual template, my Plotly dark plus presentation modes. And then I want to set a width and a height. And hopefully this gives us something. That should be make subplots. So to find our ultimate controller gain, we need to find the point where we see continuous oscillations. So I'm going to increase this to 20. And that is not looking very continuous, so let's go in between to 15. And it's dying out, so it should be higher than that. We're going to guess 18 this time. So it's growing, and we want it to be kind of constant. So I'm going to say we're pretty close, probably. Let's do 17 and a half. Needs to be a little bit higher. Slightly higher. And that looks pretty constant. And that's how we guess and check for our ultimate controller gain. So now instead of saying that Kc is equal to that, we're going to say Kcu, the ultimate controller gain, is equal to 17.85. And now we would like to include the integral portion of our controller. We have our ultimate controller gain that we just found right here, roughly about 17.85. And eventually we're going to have an ultimate period. For now, I'm just going to set that equal to 1, but we need to find this. And we don't need to make a guess for Kc any longer. So I got rid of that comment. And our GC, like we said earlier, if it was just proportional, like we did for testing to find the ultimate controller gain, it would be this, but we also have the integral part of our controller. So we need to multiply by 1 divided by tau I times S. and our Kc is equal to some value times Kcu. Our tau I is equal to some value times our Tu. And I'm just going to use Wikipedia as my reference, but our control type is a PI controller. Our Kp is 0.45 times Ku, which Ku is our Kcu. So we have 0.45 times Kcu. And then for our integral controller, we have 0.8333 times our Tu. So I'm just going to do that. And I just realized I found our ultimate controller gain, but I did not find the ultimate period, which I can just go back and do that. So I'm going to update this after that line and say GC is equal to our ultimate controller gain that we found. And then we should get the same graph we saw earlier. And in order to find our period, we just need to subtract two of these values. So we have, I'll just open up a calculator. We have 6.85 there, and then over here 6.51. And it looks like that gives us 0.34. Let's check another one just to make sure. I'm going to check kind of earlier on. $0.35 for that. Alright, so it looks like it's about 0.35. It might be between 0.34 and 0.35 depending. So I'm going to get rid of this. We found our ultimate period to be 0.35. And now we can continue. Basically, now that we've found our ultimate controller gain and period, we want to simulate the response of this system. I might need to add something else, I'm not entirely sure, but now that this is updated and we have these values here, it should hopefully correctly simulate our closed loop response. I did make an error just while I was typing in our Kc. This should be 1, and we calculated or derived this earlier. 1 plus 1 divided by the tau I times s. And our tau I is the 0.833 times the ultimate period. So let's see if that looks better. And that does look significantly better. This is what our simulation looks like. Just for fun, let's set a Kcu value that we know is not correct. So let's do 10. Run that. And as you can see, we don't reach it as fast. If we go way too high, obviously we're going to have problems. Now if I change our Tu, let's say I make it 8.35 instead of 0.35, we clearly have an issue there. So I'm going to keep that like that, right there. So that is our simulation of the closed loop response of this system using the Ziegler-Nichols control parameters that I kind of went in to detail through right here. Our next step is to repeat D2, but we want to use the Smith-Corripio ITAE open loop tuning method instead of the Ziegler-Nichols tuning method. So I'm going to start a new block here. just for my kind of sanity, I'm going to copy and paste those givens just so that I have them in this code all together. These are those parameters that we need to follow. Here, we are using a PI controller. So these are our A and B values. That I will go into what that means in a minute. We're given those, and we're going to call that PA and PB. So the proportional for A, proportional for B that we're given. We have 0.859 and 0.674. And I just realized I was actually looking at a disturbance input, but we are not doing that. We are doing a set point input. So actually our P should be 0.586. And so that's our PA. Our PB is negative 0.916. And then IA, so this is the integral controller portion. Our I is 1.03, and our B is negative 0.165. Then we want to calculate the dimensionless term based on the ratio of dead time to the time constant. So we would have PA times theta divided by tau to the power of PB. Our KC controller gain is going to be y over k. The integral time tau I is going to be equal to tau divided by that IA plus IB times theta over tau. GC, as we defined earlier, I can actually just take it from the Ziegler-Nichols code, because those should be mainly the same, so I'm actually going to take those and just double check that they look okay. So we have a 1 plus 1 over tau IS. Our GP is k times e to the negative theta s over tau s plus 1. That looks okay. And then our closed loop is GC times GP divided by 1 plus GC times GP, so that looks good as well. And we don't need to change any of that. That's the same from the previous portion. And for this right here, I think most of it is going to be exactly the same. We just calculated our other values differently, so I actually should be able to plot this the same way. But I do want to change the titles really quickly. So we have the Smith-Corripio ITAE PI control, and this is the same thing but open loop tuning response. I'm gonna run this and see. So this looks pretty good. Essentially, we use these predetermined A and B values for our proportional and integral controller, and use this design relation right here and here to calculate our values. And just comparing the two, we can see that in roughly, I guess, like not half the amount of time, but almost, this one is faster. and it also doesn't have any like kind of oscillations at the beginning, but they're both, I guess I should say they're both both methods work. They are just different methods. This second method is nice because we didn't have to guess and check for our ultimate controller gain, so it was a bit faster, but they both work like I said. So to kind of wrap up this part, basically we started by looking at how dead time looks in the S domain or Laplace domain, however you want to put that, and how it impacts our system. We looked at a first order plus dead time system using two different tools. We looked at the Ziegler-Nichols, which was more of an empirical tool, and the Smith-Corripio ITAE method, which was more of an analytical tool. And this was using both the closed loop and open loop tuning, which gives you kind of a flexibility to choose whichever tool you want for kind of for your problem. Thank you for watching, and homework 4 will be out very soon.